Earlier in the course, we talked about train test as a good way of preventing overfitting and actually measuring how well your model can perform on data it's never seen before. We can take that to the next level with a technique called k-fold cross-validation, and we'll talk about that next. It's an important tool in your tool chest for fighting overfitting. So let's talk about another powerful tool in your arsenal for fighting overfitting, k-fold cross-validation. And you may remember that we talked about train test earlier in this course about a good way of fighting overfitting as well. K-fold cross-validation makes train test even better, so let's learn how that works. So if you recall from train test, the idea was that we split all of our data that we're building a machine learning model based off of into two segments, a training data set and a test data set. The idea is that we train our model using only the data in our training data set, and then we evaluate its performance using the data that we reserved for our test data set. That prevents us from overfitting to the data that we have because we're testing the model against data that it's never seen before. However, train test still has its limitations. You could still end up overfitting to your specific train test split. Maybe your training dataset isn't really representative of the entire dataset, and too much stuff ended up in your training dataset that skews things. So that's where k-fold cross-validation comes in. It takes train test and kicks it up a notch. So the idea, although it sounds complicated, is fairly simple. Instead of dividing our data into two buckets, one for training and one for testing, we divide it into k buckets. For each bucket, we'll use that bucket as our test data set, and we use the remaining data as our training data. We then measure the resulting R-squared error score from using that bucket as our test data. Then we move on to the next of our k buckets, and we use it as our test data, and the remaining k-1 buckets as our training data, and we measure the error again. We keep doing this until we've tried using all k buckets as our test set, and we just average all the R-squared scores that we ended up with to get a more robust measure of our model's accuracy. And that's all it is. K-fold cross-validation is a more robust way of doing train test, and that's one way of doing it. There are other variations on this. For example, you could reserve one bucket as your test data, and then train against the remaining individual buckets and average those scores together. But the technique described in this slide is how scikit-learn does it, and that's what we're going to play with next. So fortunately, scikit-learn makes this very easy to do, and it's even easier than doing normal train test. It's extremely simple to do k-fold cross-validation, so you may as well just do it. Now the way this all works in practice is, you'll have a model that you're trying to tune, and you'll have different variations of that model or different parameters that you might want to tweak on it. For example, the degree of polynomial for a polynomial fit. So the idea is to try different values of your model, different variations, measure them all using k-fold cross-validation, and find the one that minimizes error against your test data set, and that's kind of your sweet spot there. So in practice, you want to use k-fold cross-validation to measure the accuracy of your model against a test data set and just keep refining that model, keep trying different values within it, keep trying different variations of that model, or maybe even different models entirely until you find the technique that reduces the error the most using k-fold cross-validation. Let's go dive into an example and see how it works. We're going to apply this to our iris dataset again, revisiting SVC, and we'll play with k-fold cross-validation and see how simple it is. Let's actually put k-fold cross-validation and train test into practice here using some real Python code. You'll see it's actually very easy to use, which is a good thing because this is a technique you should be using to measure the accuracy, the effectiveness of your models in supervised learning. So go ahead and open up the k-fold cross-validation notebook and follow along if you will. And we're going to look at the iris dataset again. Remember, we introduced this when we talked about dimensionality reduction. And just to refresh your memory, the iris dataset contains a set of 150 iris flower measurements, where each flower has a length and width of its petal and a length and width of its sepal. And then we also know which one of 3 different species of iris each flower belongs to. So the challenge here is to create a model that can successfully predict the species of an iris flower just given the length and width of its petal and sepal. Okay? So let's go ahead and do that. We're going to use the SVC model. If you remember back again, that's just a way of classifying data. That's pretty robust. There's a lecture on that if you need to go refresh your memory. So what we're going to do is use the cross-validation library from scikit-learn, and we're going to start by just doing a conventional train test split, just a single train test split, and see how that will work. To do that, we have a train test split function that makes it pretty easy. So the way this works is we can feed train test split a set of feature data, iris.data just contains all the actual measurements of each flower, and iris.target, which is basically the thing we're trying to predict. So in this case, it contains all of the species for each flower. And our test size here says what percentage do we want in train versus test. So 0.4 means we're going to extract 40% of that data randomly for testing purposes and use 60% for training purposes. And what this gives us back is 4 data sets, basically a training data set and a test data set for both the feature data and the target data. So xtrain ends up containing 60% of our iris measurements, and xtest contains 40% of the measurements used for testing the results of our model. And ytrain and ytest contain the actual species for each one of those segments. So we'll go ahead and build a SVC model for predicting iris species given their measurements here. And you'll see that we're building that only using the training data. So we're going to fit this SVC model using a linear kernel, using only the training feature data and the training species data, target data. And we're going to call that model CLF. Now we can call the score function on CLF to just measure its performance against our test data set. So we're going to score this model against the test data we reserved for the iris measurements and the test iris species and see how well it does. And it turns out it does really well. Over 96% of the time, our model is able to correctly predict the species of an iris that it had never seen before, just based on the measurements of that iris. So that's pretty cool. But this is a fairly small data set, about 150 flowers if I remember right. So we're only using 60% of 150 flowers for training and only 40% of 150 flowers for testing. These are still fairly small numbers, so we could still be overfitting to our specific train test split that we made. So let's use k-fold cross-validation to protect against that. And it turns out that using k-fold cross-validation, even though it's a more robust technique, is actually even easier to use than train test. So that's pretty cool. So let's see how that works. So we have a model already, a SVC model that we defined for this prediction. And all you need to do is call cross-val score on the cross-validation package. So you pass it in a model of a given type and the entire data set that you have. So this is all of my feature data and all of my target data, all of the measurements, all of the species. And we're going to say I want a cross-validation folds of 5. And that means it's actually going to use 5 different training data sets, okay, while reserving one for testing. Basically, it's going to run it 5 times. And that's all we need to do. That will automatically evaluate our model against the entire data set, split up 5 different ways, and give us back the individual results. So if we print back the output of that, it gives us back a list of the actual error metric from each one of those iterations, each one of those folds. And we can average those together to get an overall error metric based on k-fold cross-validation. And when we do this over 5 folds, we can see that our results are even better than we thought, 98% accuracy. So that's pretty cool. In fact, in a couple of the runs, we had perfect accuracy. So pretty amazing stuff. So let's see if we can do even better. You know, we're using a linear kernel here. What if we used a polynomial kernel and got even fancier? Will that be overfitting, or will it actually better fit the data that we have? Kind of depends on whether there's actually a linear relationship or a polynomial relationship between these petal measurements and the actual species or not. So let's try that out. We'll just run this all again using the same technique, but this time we're going to use a polynomial kernel. And we'll do the same thing. We'll fit that to our training data set, and it doesn't really matter what you fit it to in this case, because cross-val score will just keep rerunning it for you. And it turns out that when we use a polynomial fit, we end up with an overall score that's even lower than our original run. So this tells us that the polynomial kernel is probably overfitting. When we use k-fold cross-validation, it reveals an actual lower score than with our linear kernel. And the important point here is that if we had just used a single train test split, we wouldn't have realized that. We would have actually gotten the same result if we just did a single train test split here as we did on the linear kernel. So we might inadvertently be overfitting our data there and not have even known it had we not used k-fold cross-validation. So good example here of where k-fold comes to the rescue and warns you of overfitting, where a single train test split might not have caught that. So keep that in your tool chest. If you want to play around with this some more, go ahead and try different degrees. So we tried, you can actually specify a different number of degrees. The default is 3 degrees for the polynomial kernel, but you can try a different. You can try 2. Does that do better? If you go down to 1, that degrades basically to a linear kernel, right? So maybe there is still a polynomial relationship, but maybe it's only a second-degree polynomial. So go find out. Try it out and see what you get back. So go play around with that. That's k-fold cross-validation. That's k-fold cross-validation. As you can see, it's very easy to use thanks to scikit-learn, so use it. It's an important way to measure how good your model is in a very robust manner.